So you see, inverse time design, inverse design, backward resolution of dynamical systems is probably the simplest inverse problem you can think of, right? There are many, many reasons for handling these problems. For instance, you will recall how, back in 2013, it was the, planet Earth year, right? Where, many countries, many institutions celebrated different workshops, events about, the mathematics of planet Earth, oriented to different topics, geosciences, water, space, climatology, meteorology. There are so many fields of mathematics, math, biology that are in interaction with life and the nature and the future of our planet. And of course, one of the big topics in that say special year was to gain understanding through mathematical modeling of the processes in our nature. And then, of course, the key words are modeling. But, whenever you talk about modeling, oftentimes you need also to tackle issues related to inverse problems, parameter identification, right, which are related to the extra need one experiences of making models more precise, right? You can say, well, meteorology is about fluids. Well, yes, it will be some modeling fluid mechanics like Navier-Stokes, yet you have to tune the parameters, right? The viscosity, the density, and many others. So specific examples where this very issue of inversion with respect to time arises in this broad context. Probably the first and the most relevant example will be the Big Bang, right? So Big Bang research, when people do research about the origin of the universe, somehow they are solving a differential equation backwards, right, in time, right? So when, the most celebrated astrophysicists say, well, we have determined that, the Big Bang occurred, as many light years from now, going backwards, towards the past. Probably the way I understand it, right, is that they are solving a huge geometric nonlinear PDE backwards in time in order to determine at which time, this singularity, this kind of huge Dirac delta arose that led eventually by forward evolution to the universe the way we know it today. So you can guess that this is certainly not an easy problem, given that from a partial differential equations perspectives, we have still difficulties to understand, for instance, the dynamics of Navier-Stokes in 3D. We don't know whether singularities occur or not. And even in more simpler problems in, nonlinear diffusion, nonlinear waves, the classical research we all do in partial differential equations, even when you are able to show that singularities occur forward in time, that solutions do blow up, it's often much harder to say when this blow up is occurring, right? So this is why I admire so much people working in Big Bang theory and being able to determine the number of, light years, right, on which this singularity occurred. Okay, so climate modeling, climate change is also one of the great concerns of humanity. Plenty of research has been devoted to this. And as you know, one of still controversial issues, surprisingly, is that people accept that humans had some, had a major effect on this process of climate change. Again, it was about going backwards, right, on research to try to understand why, this climate change was occurring, what were the initial causes, and how, in particular, human action has been a continuous source somehow, in this case, quite negative control, right? Negative control, negative input in order to generate this climate change process. There are many applications of time inversion to, meteorological, natural resources management issues. One of the most fascinating engineering construction is probably this times barrier, right, in London, where due to the regular floodings that were occurring in the Thames River that were making, the navigation, river navigation impossible, right? They decided to build this barrier, right, that prevents the flooding to occur, in the port area. So whenever a massive, say, huge mass of water is detected in the North Pole, traveling towards the British Islands, right, then immediately there is a protocol of simulation that is launched in order to anticipate when this huge wave will reach the Thames estuary, and to determine, right, what is the expected, impact that this might have, to determine whether they should close the gate or not. Of course, closing this barrier is not for free. Whenever, they decide to close this barrier, this will, stop, traffic of ships for 1 or 2 days, and this induces tremendous commercial loss, right? So therefore, the decision of closing the barrier is very critical, and again, is kind of an inverse design problem in order to figure out what the impact could be in case this massive amount of water will get to the Thames estuary. The origin of tsunamis is again another, say, time inversion project. And actually, the application by which I was motivated to work on this topic, maybe 15 years back or so, it was during the PhD thesis of one of our former students, Francisco Palacios, at that time in Madrid. Francisco Palacios now is one of the leading engineers in Boeing, right, in the state of Washington. In Seattle, in the US, right? At the time, he was writing the PhD thesis with us, and we were interested on this paper by another Spaniard, Professor Juan Alonso, professor in aeronautics in Stanford, right? Where they were describing, this is a delicious paper, I recommend you to have a look, right? Where they were analyzing, describing the challenges, right, of the future technology of supersonic aircrafts, right? And then, as we know, we had in the past, the French Concords, right? So, at a given time, this technology became not sufficiently safe and, environmentally friendly, and it was stopped. Right. So now we are working in a generation of supersonic aircraft that will be much more, safe, right, and also environmentally friendly. And in this paper, they describe how the main challenge, one of the main challenges for the new generation of supersonic aircrafts, is to diminish the sonic boom, right? So in the age of Concorde, right, the Concorde was not allowed to fly supersonic on populated areas, right? Because the sonic boom it was generating was too large in amplitude, not acceptable for human beings, right? So it was only allowed to fly supersonic on unpopulated areas, which made, of course, the path of the Concorde to be suboptimal, because they were not really being able to exploit fully the supersonic capacity. So the challenge for the new generation of supersonic aircrafts was to succeed on, designs that will make this sonic boom to be mitigated so that when getting to Earth, it will be acceptable according to, present regulations, and in this way allow the supersonic aircraft to fly also supersonic on populated areas. And this is a problem about inverse design. Why? Because as is indicated in this drawing, right, the supersonic aircraft, according to the shape it has, produces an initial signature of the sonic boom that propagates towards Earth, right, according to, say, a version of simplified PDE, which is kind of a nonlinear Vargas equation that was introduced at the time by Witham, right? And then, this initial signature propagates according to this kind of nonlinear Vargas equation to reach Earth. So the question that is formulated about the design of the shape of this new generation of supersonic aircraft is about how to design the shape of this, say, aircraft so that the initial signature is adequate to guarantee that when reaching, at the final time, right, Earth, this signature will be admissible. So in some sense, as you see, is kind of solving the PDE backwards, right? So to identify what are the initial conditions that make the solution at the final time, so the signature of the sonic boom when reaching Earth, the solution at the final time to be admissible to fulfill some constraint, okay? So research, this paper was published back in 2012, I think. Sorry that I don't see it here with the bar. 2012, so 12 years ago. 12 years later, right, very recently, there was this newspaper article saying, well, these airplanes now exist. They are not being yet commercially used, right? But they are being tested to really check whether, the technology that has been developed, so to minimize the sonic boom, right, is sufficiently adequate so to allow, these aircrafts to fly supersonic over populated areas. And you can find easily several news, very, very recent news. This was a couple of weeks ago about, the immediate future of this new generation of supersonic flights, right? So you see that here in this article, they indicate that they are aiming to become operational before 2030, right? So we are talking about an horizon of 5 or 6 years. Well, even if this happens, I'm not sure we'll be, as mathematicians at the university, able to, to enjoy, these fast trips that will indeed facilitate a lot commuting and communication, because I suspect the prices will not be that cheap, right? But this is a different issue. Okay, so now, how do we formulate this class of problems mathematically? Well, is very easy, right? You say, okay, let's take our, the models we have in mind. So just to write it down in an abstract manner, we say, okay, ut plus au equals 0. Of course, I could make it to be time dependent, right? To be non-autonomous. This can be linear, can be nonlinear, can be a PDE, can be an algebraic system or a finite dimensional nonlinear dynamics, right? So you can think here on, the Lorentz system in meteorology or the Navier-Stokes equations you like, or nonlinear Schrodinger or wave equations, the model you have in mind, okay? And then time inversion, which, as I said, is the simplest inverse problem, in which, because we are simply trying to inverse the sense of time, reverse the sense of time, this time inversion problem can be formulated, okay, it's after all a Cauchy problem, except that classically for Cauchy problems, we give the initial datum and we try to, describe, anticipate, analyze the future evolution of the solution. So here we are just reversing the sense of time. And what we do is that we give the final value of the solution, right? And then we try to collect the solution backwards in time, right? And in particular, you can think of, given the time interval t from 0 to the future capital T, if the classical, analysis of PDEs we do is to determine the future at time capital T out of the initial data at t equals 0, here we do the opposite. Out of the final time, the value at the final time ut, we try to recover the value at the initial time. Then, okay, of course, there are different scenarios you may encounter. Maybe the most favorable one is the one of the linear or nicely nonlinear wave-like equations. This is the acoustic wave propagation equation, or the equation for acoustic waves, the vibration of a one-dimensional string or a two-dimensional membrane. The classical wave equation has many applications, but we are also used here to consider the simplest possible case, although what I'm saying applies for a much broader class of wave-like models. We consider the linear constant coefficient wave equation with, if you wish, Dirichlet linear boundary conditions, right? And then we say, well, in this case, time inversion is a trivial problem. Why? Because the model is purely, right? The model is purely conservative. Therefore, I can, both apply the classical theory, whatever the method you have developed is, Fourier series, semigroup theory, Galerkin-like kind of approximation methods. You can apply it equally forward and backward in time. This is actually an infinite dimensional Hamiltonian system where energy is conserved, right? And reversing time, you can equally solve this equation, the PDE, backwards than you do it forward. So no difficulty at this point, right? You can apply the same analysis, the same computational methods for solving this wave equation backwards, because it's a time reversible model, okay? Now, of course, for the wave equation, you are experts on this. Many of the attendees to this workshop are experts on this. You can consider more sophisticated problems, like, for instance, controlling wave propagation through sensors and actuators. And in that setting, in this broad context of control theory for wave propagation, the problem of observability emerges, right, is the classical one in which you are trying to determine whether, say, you can recover the full energy of the solution out of partial measurements. As you know, these problems are much more tricky, right? But they can also be considered as part of this kind of general frame of inverse problems we are considering here, right? Except that in that case, when you are dealing with observability, you are often trying to recover the full, say, information on the solution out of measurements done, for instance, on the boundary or near the boundary of the domain where waves propagate. Time inversion is much easier. I give you the final state. I'm just asking you whether you can recover the initial state. And then in that case, you say, for wave equation, no problem. The model is time reversible, and I can apply the classical theory for the Cauchy problem and also the numerical algorithms, okay? Things get trickier when you deal with the heat equation. Again, to simplify the presentation, I consider the linear constant coefficient heat equation with zero boundary conditions, right? And then I try to address the problem of backward resolution. We have to be careful there, right? Because we know, and this is something we learned, in the first PDE course, that solving heat equations backwards in time is an ill-posed problem, is a prototype of ill-posed problem, and we all know this, but often we don't pay sufficient attention to what that means, right? So in order to understand what that means, let's check what happens if I really try, right? If I really try to solve the heat equation backwards in time, right? So assume, we are dealing with this heat process from time 0 to time infinity, and I give you the measurement of the solution today. Today is capital T, okay? And then I ask you, what can you say about the initial datum, the solution of this heat equation, say, yesterday or a few days ago? So you have to go backwards in time. Then you can use the Fourier expansion of the solution, and what you realize is that the L2 norm, which is a very natural quantity for measure the solution you have today, right? The L2 norm of the solution today in a Fourier basis, on the basis of eigenfunctions of the Laplacian, right, is giving you information about the Fourier coefficients in the past, but weighted with these weights that are decreasing exponentially as k, the frequency increases, right? So you know by Wiles' theorem that the eigenvalues of the Laplacian lambda k grow, right, polynomially as k goes to infinity. In 1D, lambda k is of the order of k squared, in 2D is of the order of k, and so on. In general, the power is 2 divided by the dimension, the space dimension of the domain omega. So, but this is not so relevant here. These eigenvalues grow polynomially, but what is the key here is that this is exponentially flat. So if I ask you then, what can you say about the initial datum, given the information that the solution today is in L2? I ask you, can you guarantee that this initial datum is in L2? And then you will tell me, of course not, because, for being in L2, I will need all these ways to be bounded below, and they are not. Okay, so then I ask you, can you guarantee that the initial datum is in some negative Sobolev space H minus S? And you will tell me no either, because in order to guarantee that the initial datum is in the space H minus S, I could only allow here a polynomial degeneracy on lambda k to the power minus 2s, but never polynomial. So you see that when trying to solve the heat equation backwards, you are losing plenty of information, and in particular, you cannot expect to have any kind of stability or well-posed property in any Sobolev setting, right? And of course, things don't change if you give me here the information in a Sobolev space. Say you say, well, let me make measurements sharper at time capital T today. I give you information in H25. Okay, good. H25, then you will have here lambda k to the power 50, yet this is not good enough, right? Because the degeneracy will remain exponential, right? And this is precisely what motivates this very fact that the heat equation is a prototype of ill-posedness. You can think also in terms of the classical Cauchy problem, right? Where we rather think on solving the equation using the Gaussian convolution, and you encounter similar difficulties, right? Because, and this is something that is well known in image processing, while the convolution is very nice in the forward sense of time, then is very, very, very hard to undo, right? This is in material sciences, right? Mixing materials is something you can do, but once the materials are mixed, they are not. I mean, this is a process that is highly irreversible, and it's not because you rotate, the mechanism in the backward direction that these two mixed materials will dissociate again. Okay, so well, as I said, if you look to the classical definition of well-posedness in the sense of Hadamard, you will encounter that the heat equation is one of the most, say, tragic examples, right, in which this well-posedness is broken, right? So well-posedness in the sense of Hadamard means that there is existence and uniqueness of solutions, and also some sort of stability in the sense that the regularity of the solution will be preserved, the trajectory will remain always within a given, say, Hilbert or Banach space we can identify. And this is precisely what is broken by the heat equation, because every, solution in the backward sense of time will escape any reasonable space you can think of. Okay? So then this is kind of a catastrophe. What can we do? Can we still, figure out whether we can give some estimates? Can we somehow explain an upper bound for this catastrophe that is occurring in the backward sense of time? And the answer is yes. So you can do that in several ways. In the specific example I was considering here, you have Fourier series expansion, and with Fourier series you have a complete description of the process, both forward and backward in time, and therefore you can, represent in these exponentially evolving Fourier coefficients how things occur. But of course, as we know, Fourier series will not apply as soon as the coefficients of the PDE are depending on time, or when the PDE is, say, nonlinear. What can we do then? Well, we like very much to develop energy estimates, right? Actually, this has been done also using Carleman inequalities, one of the tools that is prototypical in addressing inverse problems. So these Carleman inequalities were applied for the time inversion in a classical paper by Jacques-Louis, right? But later on, there was this proof that I think was given by Luc Tartar, right? And that I am reproducing here, right? So this is something that is extremely nice. Of course, it's a bit naive, right? There are only a few inverse problems you can solve with this technique, but it really, goes to the heart of what ill-posedness means, right? So let's proceed. So I try to do energy estimates for the heat equation, these times backwards in time. And for this, I proceed as classically. I multiply the heat equation by the state y. I integrate by parsing the Laplacian, and I get this classical energy identity. This is an identity, right? So I say that half of the time derivative of the square of the L2 norm plus the square of the H1 norm is equal to 0. And then you see here the parabolic structure of the problem, because you see that the L2 norm is being dissipated forward in time, dissipated, and therefore backward in time enhanced by a superior quantity, which is the H1 norm, right? So you see that you are therefore damping forward in time or enhancing backward in time the L2 norm by a higher order norm in H1. And this anticipates the difficulties we have to control the process backwards. Okay, anyhow, to better understand how this process goes, the best we can do is to write it down as an identity for the L2 norm. And for doing this, the only thing you need to do is to introduce this Rayleigh quotient, capital lambda of t, which is just the quotient, so there is a bar missing here, is the quotient between the L2 square norm of the gradient divided by the L2 norm of y, right? So this Rayleigh quotient is also called in this context the frequency number. And why is this called frequency number in this time inversion context? It is called the frequency number because, in particular, when y were written in Fourier series, if you have had a finite number of Fourier components on y, right? So here you will have seen the largest eigenvalue entering in the Fourier expansion of the solution y. Okay, fantastic. Now, what do we do normally when we prove that the heat equation is well posed forward in time and even that it decays exponentially? When we use the Poincare inequality that says this quotient, I insist, this should be really a quotient, there should be a bar here, right? This quotient is bounded below by the first eigenvalue lambda 1 of the Laplacian, which is positive. And this is so simply because, according to the classical mean mass principle, the first eigenvalue lambda 1 is the minimum of this frequency number among all possible functions y in H10 omega. Good. But this is good for solving the heat equation backwards, right? We have an upper bound for lambda that we can put on the right-hand side as being a damping term. And this leads to the exponential minus lambda 1 t decay of the L2 norm of the solution. Very good. But you see, here, this will be the forward resolution. But here now, we want to, prove something in the backward sense. So you see, in order to prove an estimate in the backward sense, we will need an upper bound now on the Rayleigh quotient. And of course, there is not upper bound for the Rayleigh quotient. There is a clear lower bound, the Poincare constant, but there is not upper bound simply because the H1 norm is stronger than the L2 norm. We don't have the reverse of the Poincare inequality, right? When you increase the frequency number, the eigenfunction, this quotient goes to infinitely rapidly. So it is, in principle, it seems like impossible, right? It seems impossible to get an upper bound for this frequency number. There is, however, a critical observation. And the observation is also, very much coherent with our understanding of the solution in Fourier series, right? The observation is the following, and this is a good exercise you can try to do. Take this frequency number, this ratio, because there is, again, I insist, a fraction bar here missing. Take this quotient, compute the time derivative, do it carefully, use integration by parts and the solution, the fact that you are dealing with a solution of the heat equation, and miracle, what you observe is that the frequency number decreases along the solutions of the heat equation. So what this decrease of the frequency number is telling you is that in this model of the heat equation, there is not something like turbulence or so. The complexity of the initial data is going down. And this, of course, in the context of Fourier series, is very easy to observe. If you give me an initial datum in which only 13 eigenfunctions are involved, the future evolution of this solution is also dominated, totally described by these 13 modes. So complexity cannot increase. So in this case, this is a very naive computation. You can extend it to much more general heat-like equations where you will have more complicated bounds, like Gromval-like bounds. But still, what is the key is that even though you cannot expect to get an upper bound for this Rayleigh quotient globally in the space of finite energy functions, you do have this bound when you are dealing about a specific trajectory of a heat-like equation. And because of that, because you have the upper bound, you can reverse the classical energy inequality and you can get the estimate in the backward sense of time. And then you say, well, how can it be? Well, it can be because you see this backward, right, estimate in which out of the L2 norm in the future, you can estimate the L2 norm in the past depends, right, also on the initial datum itself. So it's not a global estimate as we are used to, but it's an estimate that depends implicitly on the solution you are considering. So this can be viewed as a logarithmic interpolation inequality, right? And therefore it has a nonlinear nature, and it's just a way of mimicking when you look to this inequality in Fourier series, you see that it says exactly what you observe in the Fourier series representation. So it's an energy way of recovering and extending the estimates that the Fourier series provides. But still, this is fully compatible with the very ill-posed nature of the backward heat equation, right? So now, as I said, this is an inverse problem. And inverse problems, as you know, this is a huge field where very often there is a significant gap between theory and numerics, right? So for inverse problems, there are beautiful theories based on analytic expansions, Cauchy-Kovalevska, Carleman inequalities, geometric optics. There are many different tools that have been from analysis that have been developed to deal with inverse problems. However, when you get to computational practice, right, much less is known, and people, often adopt a discrete perspective, meaning, okay, yes, the inverse problem is formulated in a PDE setting, but after all, I will discretize everything through finite elements, for instance. I will consider a finite dimensional model, and then the inverse problem consists on identifying some parameters, something that I will do using some least square approach, right? So what is the least square approach in this context in which we are trying to identify data for a dynamical system, in which the goal is that the solution at the final time reaches, right, some desired target. So UD, the desired target, or you can think D as being data as well. UD is the data you have measured today, right? And then you want to identify the initial datum so that the evolution of the system, so the initial datum that was sometime in the past. So what was the initial datum in the past at time t equals 0 that led through the evolution of this system to the measurement, the data you are observing today, UD, right? So how do you do that? Well, you just say, okay, let me minimize the gap. So among all possible U zeros in wherever the Banach space or Hilbert space of initial data you are considering is, try to find the U zero so that the solution starting from U0 at the time capital T, UT, is the closest possible to UD. So just minimize the norm. This is a least square approach. Or if you want to, you can also compare this with the classical strategies for solving ODEs and PDEs, like, for instance, the Shurin method, in which, right, for instance, for solving the Sturley-Liouville problem, you choose the initial data, you shoot the initial data in different directions, right, hoping that the solution of the evolution problem will match the given, say, measurement. Okay, this is what, in practice, we can try to do. So let's try to do it. Let me show you a numerical experiment trying to implement this, on one hand, natural, on the other hand, naive perspective to the numerical inversion of the heat equation, right? So this numerical experiment was developed by Alejandro Pozo, that was a former PhD student in our team in Bilbao. Now he's working in the Basque industry in some artificial intelligence company. And so let me explain you what Alejandro did, right? So Alejandro said, listen, we will do the following experiment. I just dealing with the heat equation in one space dimension, right? In some, space interval. And then I tell you the target is this kind of Gaussian-like blue profile, okay? So how Alejandro generated this profile at the final time? Time here is 1. So the heat equation is evolving from t equals 0 to capital T equal 1. And what we say is, listen, I have measured today, I got today to the lake. I measured the concentration of pollutant in the lake. and I have observed this kind of blue, say, Gaussian profile. Okay, so in this Gaussian profile, you see that the value at the left is 0, the value to the right is 0, 1, but this is a very nice, right, smooth profile. Okay, of course, we are doing here a computational experiment. So actually, this blue Gaussian profile at the final time was generated by an initial datum that I can explicitly compute. So the initial datum that Alejandro took was the black one here, right? Where you have this broken line, 0 linear to the top, and then down again, and then constant again. So this kind of triangle, right, by Gaussian evolution, and this is something we all expect, right, by Gaussian diffusion, becomes at the final time this blue line. Okay? But now, what is the computational exercise? The computational exercise is now I erase this black initial datum. I just give you the blue measurement of today, and then I ask you, can you please tell me what the initial datum was yesterday at t equals 0? Then you will say, okay, fine, no problem. I will implement the least square method mentioned before, right, by producing some kind of finite difference or finite element approximation of the heat equation. Okay? And this is what Alejandro did to show why things are tricky. So because you are minimizing a nice quadratic functional, you can apply some kind of steepest descent algorithm, right? You just compute the gradient, right, of the functional. As you know, the gradient of the functional is related with the adjoint. The evolution of the adjoint will be seen here, but this is not that relevant, right? So what is really relevant is to see how in green, right, iteration by iteration, so we see here the number of iterations, 300, we see here on the vertical how the value of the functional is going down because we are minimizing the gap to the target, right? So along iterations, the functional goes down, and while the functional goes down, we expect, of course, that our algorithm will be able to discover that the green line U0, the computational green line, should be very, very close to this black triangle. Okay? Let's see what happens then. Let's then run the numerical simulation and see what happens. Okay, so you see in red, you see how the red line is approaching the blue line. And the green line is trying to approach this triangle function, right? So the functional here on the right is going down, but we see how after 100 iterations or 50, it slows down, right? And then there is a threshold after which, the gradient has tremendous difficulties to evolve down, right? This is precisely the impact of the ill-posedness of the heat equation. We see it in several aspects, right? So first of all is that, the gradient descent algorithms, even if we optimize the step size, and we do it here in a rather oscillatory manner because the computer doesn't really understand why, we have difficulties to get closer to the target, right? Despite of these oscillations in the step size, the functional has difficulties to really get to the well, to 0, right? That should be the minimum of this functional. And this you observe it on the green line you get. Of course, the computer is smart enough to realize we should generate something like a triangle, right? But in practice, we don't get a triangle. We get kind of a smooth approximation of the triangle, which is this green line, right? Which is, still quite far from the initial correct configuration. Now, if instead of asking me whether I am satisfied by this simulation by looking to the initial datum, because I am not, I see a significant gap between the true initial datum, the peak initial datum in black, and the computational initial datum in green, despite I'm not satisfied by the level of resolution at the initial datum, I see that at the final time, the target in blue is well achieved. Actually, you cannot distinguish the red line and the blue line. This is why? Well, this is because of the very dissipative effect of the heat equation that makes that the initial gap, right, is really diminished so that at the final time you nearly don't observe this gap. But if your goal was, and as it was, right, if your goal were as it was, recovering the initial datum, you see that there is a substantial gap. And this is precisely due to the ill-posedness. We have seen both in Fourier series and backward energy estimates that backward energy estimates are exponentially growing. And this is something that the computer doesn't understand. If you want to run your numerical simulation in a stable manner, you have to chop off these high frequencies. And this is what the Tikhonov regularization does. But once you introduce this Tikhonov regularization, you are getting away from the actual minimizer, and this is why you get the green instead of the black. On the other hand, the fact that the gradient descent algorithm will soon saturate and will have difficulties to go down is already anticipated in the classical, say, analysis of the gradient descent algorithm, because the classical results for the convergence of the gradient descent algorithm tell you, listen, the gradient descent algorithm converges, but the step size you can employ on marching and the descent, the actual convergence rate, depends on the condition number. And the condition number is the ratio between the largest eigenvalue and the smallest eigenvalue of the dynamics you are considering. But here the gap is infinity, which means that we soon realize that, after a few iterations, right, the step size becomes nearly zero, and therefore progress is really negligible. Okay? Very good. So this is the manifestation, the computational manifestation of the ill-posedness of the backward resolution problem for the heat equation, right? You can claim that you avoid ill-posedness by any kind of regularization process like Tikhonov. Yes, but eventually you will pay this price, and you will pay it in terms of lack of accuracy on the reconstruction. Of course, these issues are relevant in many other contexts, in particular also for the control and the observability of the heat equation. As we mentioned before, for the wave equation, these are more sophisticated problems. The issue is, again, to reconstruct the initial datum of the heat equation, but this time out of partial measurements done, for instance, on the boundary or near the boundary of the domain, right? You need to employ more sophisticated Carleman inequalities. There is not a very simple backward energy estimate as I have done before, and you have to replace this by more sophisticated Carleman inequalities, right? But, you get similar, say, estimates with, also exponential weights, and therefore, these are processes that are also ill-posed and accordingly difficult to deal with from a computational perspective. So we can say that, within this class of linear PDEs, there are like two extreme models: the wave equation, which is perfect for time inversion, and the heat equation, which is a catastrophe. And of course, there are many intermediate models. You can combine all these effects in models like viscoelasticity. You could think on memory problems. There are many variants of these questions you could analyze, and for which both the analysis and the numerics will be interesting. Actually, because the wave and the heat equation behave in such a different way, right? In the classical math physics literature, it has been, employed at several occasions or for different purposes, a transformation that is able to link the solution of the wave equation and the heat equation. So the principle is written here. Some people call it Kanai transform, some others transmutation. This kind of transformations was used also by Charlie Pfefferman and collaborators in the 70s to analyze, the asymptotic expansion of the heat equation, on manifolds and so on. Further developing the original contribution of Varadan, who said that the heat equation on a manifold is precisely has the same structure as the Gaussian, but in which you replace the Euclidean distance by the geodesic distance within the manifold. So there is plenty of literature on this. And the principle is the following. So contrary to what we are taught in class, understanding heat equations like here, first order in time, is harder than understanding wave-like equations, which are second order in time, which is called now S to change the notation. So for wave equations, we have, time reversibility. We have propagation along characteristics or by characteristics. And this makes waves much easier to track both forward and backward in time. For heat equation, we have diffusion. Diffusion mixes everything up, and therefore diffusion is very nice when you go in the forward sense of time because you gain regularity, you gain decay, and so on, but it's impossible to solve backwards. This is why very often it is better to see the solution of the heat equation through the lens of the solution of the wave equation, and then this is the kind of transformation that does the job, right? So give me the solution for the wave equation for all values of the pseudo time s from minus infinity to plus infinity. Do a cocktail, right? Now using the one-dimensional heat kernel that transforms two s derivatives into one time derivative, as in here, this is the one-dimensional heat kernel, mix the values of the solution of the wave equation for all times s according to this Gaussian envelope, and then you get a solution of the heat equation. So this formula that is so nice is very hard to reverse. The inverse Kanai transform was introduced in this paper with Sylvain Hervedosa in ARMA 10 years back or so, right? And this Kanai transformation tells us many, many things, right? In particular, it explains why for the heat equation, the velocity of propagation is infinity. For the wave equation, the velocity of propagation is finite, 1 for the classical D'Alembert problem. But for the heat equation, the velocity of propagation is infinity. Why? Well, because according to this Kanai transform, right, the heat equation at any time is gathering, is an average of all the memory of the trajectory of the wave equation from minus infinity to plus infinity. So all waves traveling in all directions from minus infinity to plus infinity merge to compute the solution of the heat equation, which turns out to have this convolutional nature and infinite velocity of propagation. And the reason why is so hard to undo, to reverse on time, leading to this phenomenal ill-posed problem. Okay, so then you could think, well, then maybe ill-posed in the backward sense problems are exclusive to heat-like equations? Well, and the answer is no. Very often, for wave-like problems, boundary conditions that make the forward problem to be well-posed make the backward problem to be ill-posed. And you see it here by this very elementary example. You just take the one-dimensional transport equation. We could do the same for the wave equation. There are also for the wave equation in 1D, the classical transparent or perfect boundary conditions, right? That kill the semigroup. There are semigroups, wave-like semigroups that vanish in finite time, making therefore the backward resolution impossible. And this is the simplest example, just first order. The same can be done in order 2 in time. But for the first order, we take just the transport equation in the space interval 0, 1. All data are transported towards the right with velocity 1, as these green waves indicate. You can make the problem well posed by taking Dirichlet boundary condition equals 0 over the point on the extreme x equals 0. Then by characteristics, the solution becomes 0, right, after time t equal 1, because simply the initial signals are, quitting the space domain 0, 1. So you see that after time 1, whatever the initial datum is, all this initial data collapse into the 0 state, and therefore, whatever you do after time equal 1, you will never be able to reconstruct the initial datum out of the final datum. So you see that this problem of backward resolution, ill-posed backward resolution, is not exclusive to heat equations, but it can occur also for wave equations due to the interaction with boundary conditions that can act as absorbers of information that you will not be able to recover anymore. Okay? So let me then stop here. The next step is to move into nonlinear models, in which the linear phenomena we have analyzed until now will be enhanced and will make, therefore, the problem of backward resolution even harder because of the possible emergence of singularities, like in the Barger's equation I am showing you here, which is the simplest prototype of, say, equation generating singularities and shocks in one-dimensional fluid dynamics. As you know well, the theory of entropy solution for scalar conservation laws, in particular Barger's equation, is by now well established. And the theory says, well, listen, what you expect, that there is a unique entropy solution which is constituted by regular arcs connected by shocks that propagate according to the classical Rankine-Hugoniot condition as written here. This is true, and therefore, we have a good mastery again for the forward resolution of Barger's-like equations, since the pioneering works of Khrushchev, Oleinik, Lax, and so on. This is something that is perfectly well established. But of course, for us in this series of lectures, the challenge is to try to understand the problem of backward resolution. And as we will see tomorrow, we will start from this point. This is a catastrophe now of a different nature, because, in the linear heat equation, we were keeping backward uniqueness. There was a problem about stability, but here actually the catastrophe is more enhanced because we lose even backward uniqueness. So thank you for your attention. We will continue this.
So I have just one question regarding that the backward uniqueness you have shown using the property like this log convexity type. So here if you have, so you told that this methodology works if you have a coefficient with t and x also for the parabolic model, right?
Right.
So and for the wave type equation, because of the reversibility, it is already backward uniqueness is true. So if you have the variable coefficient for a coupled wave and heat, in that case, is this result will be true by this approach?
That's a very good question. So indeed, the heat equation with variable coefficients, right, was treated. So let me go back here. So here I didn't mention our paper, but there is a paper back in 2003 or so with Enrique Fernandez Cara that is called The Cost of Approximate Control of the Heat Equation, right? So we're analyzing this problem in detail. And although here, in principle, the context is Carleman inequalities, at a given time, when you want to quantify this kind of inequalities very precisely, you need to use also backward, resolution of the heat equation. And in that paper, we are considering indeed variable space-time equations. And what we show is that you have something similar like in here, except that in this first inequality that here for the pure heat equation is just a decay, for lambda you have a Gromwall inequality, okay? So you have basically the same result, but this lambda zero is more complicated, right? Because you have here a further Gromwall, right? For the value of lambda or for the frequency number. This is the heat equation with variable coefficients. Now, for wave equation with variable coefficients, you can just do energy estimates, right? Because, the same way you do forward energy estimates using Gromwall, you can do it backwards, provided, of course, the coefficients of the wave equation are regular enough. You need one derivative in time and so on. So here you can do Gromwall, and here you can do backward resolution by this kind of energy estimates involving the frequency number. Now, if you ask me about, for instance, thermoelasticity, well, I'm not sure this has been done. I remember Luz de Teresa, our former PhD student many years back, she was writing her PhD on the control of thermoelastic plates. And I recall she was facing this problem. I don't know whether this was treated in the literature or not. We should check. But you are totally right. I mean, there is some work to be done, right? When you have a coupled parabolic hyperbolic system. But I will expect Shirshendu that this should work, right? Because there is no reason why, in the presence of a wave-like component, the frequency number will evolve more dramatically than it does for the heat equation. But, well, this is also a good exercise. So let's try to do for tomorrow the backward uniqueness, quantified backward uniqueness for instance, for the system of elasticity, right? So are people familiar with the system of elasticity? I can write it down if you wish. If I have a second, I can share the iPad and then write it down. Okay, so I can write it down here, for instance. So the system of elasticity, the system of thermoelasticity, the simplest one in 1D. You can also do it in multi-D involving the Lamé operator. But in 1D will be something like UTT minus UXX plus theta x equals 0. And here you will have the heat equation, U theta XX, and if I am not wrong, here is UXT, right? And this is indeed the system of thermoelasticity, right? In which you see that the energy estimate will be you multiply here by UT, you multiply here by theta, and when you multiply here in the first one by UT, you get the classical dissipation of the energy of the solution of the wave equation, which is the integral of UT squared plus UX squared. You get a term which is the Cross term, like this. Now, when you multiply by theta, you go to the second equation, you get the time derivative of 1/2 of theta squared plus theta x squared. This is the classical dissipativity estimate for the heat equation. And then you get the cross term UXT theta equals 0. When you integrate by parts here, you pass one derivative from U to X, you gain here a minus sign, and then, right, and then these terms here, right, cancel, and then you get the classical, say, energy identity for the system of thermoelasticity, which is the integral of UT squared, UX squared plus theta squared is dissipated according to theta x squared, right? So now the question will be, of course, this gives you the decay, right? You can even prove the exponential decay of the system of thermoelasticity. In 1D, in multi-D, things are much more complicated, as discussed in a joint paper with Gilles Lebeau, right? But in 1D, it's not hard to build energy-like estimates to show that this leads to exponential decay. So if you call this energy ET, we know that for the 1D thermoelasticity equation, you have exponential decay, right? But the question is what happens backwards in time, right? So then you need to introduce some frequency number, right? Right. And the frequency number in principle should be what? The frequency number should be something like the integral of theta x squared divided by the energy of T, right? So now the question will be, get upper bounds on the frequency number n on T, right? So in principle, what do we expect when solving this kind of system of thermoelasticity? You give me some initial condition for U, you give me some initial condition for theta, they mix up and they lead to this evolution for U and theta, right? And then there is a transfer of energy from waves U into theta, right? So this is why, our human body is also thermoelastic. The elasticity properties of the fibers of our muscles change with temperature, right? And this is why also we shower when we exercise, right? There is transpiration because the temperature of our body also changes by simply, insisting on the elastic deformations, right? So there is a transfer between elastic deformations and heat and vice versa. But somehow the total frequency that is involved in the initial condition, putting together, the oscillations of the wave and the heat equation, you don't expect this to grow, right? And therefore, you expect this frequency number to remain bounded along the trajectories. Is this true? Can this be proved by some kind of, integration by parts? So by the way, for the heat equation, it is very easy, right? For the heat equation, I said that the frequency number, which is the integral of gradient theta squared divided theta squared, decreases. And the reason in this case is very simple, because if I take the time derivative of n of t, what do I get? I get the time derivative of the numerator times the denominator minus the time derivative of the denominator times the numerator, right? And divided by theta squared. So if I want to show that this is negative, it is sufficient that I analyze the sign of the numerator because the denominator is a square, is positive. So what happens to this? This times the integral of theta squared minus theta t integral of gradient theta squared. So why is this negative? Well, you see, this is what? Integrate by parts, you get minus Laplacian u times theta t. But then this is theta t is the solution of the heat equation. So theta t is Laplacian u. So you get here Laplacian theta squared. And what is theta times theta t? Theta t is the Laplacian, you integrate by parts here, and you have your gradient theta squared. So what we are saying simply is that the frequency number decreases because the following inequality is true. Right? And this is, of course, true. Why? I mean, you can take, if you wish, square roots, right? And you immediately realize that this is true. Why? Because gradient of phi squared is the integral of phi times minus Laplacian phi by integration by parts. So if you apply here Cauchy-Schwarz, you get the inequality above. So you see that for the solutions of the heat equation, using the explicit expression of the solution and elementary, interpolation inequalities and integration by parts, you can easily prove the decay of this. What we do in our paper with Fernandez-Cara is more sophisticated because we involve LP, LQ estimates and so on, also time dependent, but it's the same principle. So thanks to you.